Welcome to this lecture series in group theory. In the previous lecture, we looked at the orthogonal group of R2 in a very explicit way. We first defined what are rotations and then what are reflections, and then we saw that the orthogonal group of R2 is nothing but the union of the collection of all the rotations and the collection of all the reflections. And in fact, we also saw, maybe implicitly, I did not explicitly mention it, maybe, that the collection of all the rotations is nothing but the special orthogonal group of R2. So we defined the notion of rotations via a very geometric motivation, and I do not want to recall the definition. You can look at the previous lecture for recapitulation. And the question or the discussion of today's lecture will be centered around doing the same thing for an abstract two-dimensional real inner product space. Can we have the same treatment about rotations and reflections for an arbitrary two-dimensional real inner product space? That is the question. And that will lead us to discuss a certain linear algebraic concept. All right, so today will be a short discussion and let us proceed. Some problems for practice. And now let us get started. So let V be a two-dimensional real inner product space. And the main question that we want to talk about is, can we define rotation by theta and reflections of this object V in the same vein as we did for the Cartesian plane R2? And one can say, well, we have the definition of the special orthogonal group of V, and we also have the definition of the orthogonal group of V. The orthogonal group of V is nothing but those invertible linear maps which preserve the inner product of the vector space. And this is one cryptic way of expressing it. And the special orthogonal group is those things in the orthogonal group whose determinant is 1. And one can say that's it. These will be called rotations and these will be called rotations and reflections, and that's it. We are done. The reflections will be just those with determinant -1. So we are done. What is the issue? The issue is, like in the Cartesian plane, we had a very geometric way of expressing this. Right now it's not clear. Suppose I give you some element of SOV. Can we extract theta out of it? Is it even possible? So that is the main point, and what will happen is we will introduce a notion of orientation of a vector space. The facility that was available to us in R2 that allowed us to define rotations as we did was the implicit ordering on a certain natural basis on it. In R2, we have the standard basis, E1, E2. E1 is, of course, this vector 1, 0, and E2 is 0, 1. And in all our definitions, we had this implicit ordering available to us. E1 came before E2, and all the definitions were kind of using this implicit ordering. We were, in some sense, preferring E1 over E2, whatever that means. But in an abstract vector space V, there is no such thing. You can choose an orthonormal basis of it, but then suppose you choose V1, V2 as an orthonormal basis of V, then someone may say, okay, I will treat V1 as the first vector and V2 as the second vector and define rotations that way. But some other person may say, I'll take V2 first and V1 first. Why should I specifically prefer this guy to be the first vector or whatever? So in some sense, the x-axis for the first person might be along V1 and the y-axis along V2. And then the same discussion for R2 as for R2 goes along. And for the second person, the x-axis and the y-axis may have different roles, the opposite roles. And this is a genuine confusion or genuine point of contention. And it cannot be just overcome without introducing some extra definitions or extra structure on the vector space. So we will talk about orientation of a vector space to resolve this issue in a certain satisfactory sense. The notion of orientation is also fairly familiar to us from our high school physics, I guess. So what we do is, suppose we have this three-dimensional space, and generally we represent that via these three lines. This is the origin. And now suppose I label it like this. I say this is the x-axis, this is the y-axis, and this is the z-axis. Then in high school we learn that this is not the correct way of labeling. Why? Because what we are taught is you put the blade of your right hand along the x-axis. Then you curl your fingers along the y-axis, and then then you curl your fingers towards the y-axis, and then what you should get is that your thumb should be pointing towards the z-axis. But that is not what will happen if you label the points like this. I mean, label the axes like this. However, if you labeled them like this, x was here, y was here, and z was here, then you put the blade of your right hand palm like this, and the fingers would be pointing this way. You curl your fingers towards the y-axis, and the thumb will then be pointing along the z-axis. So this is in some sense the correct way of labeling the axes. So this is imprecise. This language of placing the palm or blade of the palm this way, that way, this is not mathematical language. We need to capture this idea mathematically, and the notion of orientation of a vector space comes to the rescue. All right. So yeah. So with that, with these two things in mind, let's first discuss what is meant by orientation of a vector space, and then we will see how we can resolve this small issue over here. And hopefully I will not forget to talk about this also. All right, so let's proceed. So now we will have a purely linear algebraic discussion, nothing to do with group theory, for some time at least. So fix an n-dimensional real vector space, and let script B be the set of all the ordered bases of the vector space V. What do I mean by that? I mean you collect all these tuples. So each Vi is a vector, all right, such that this is a basis. Or I will just say that they are linearly independent. Since the vector space is n-dimensional, the linear independence of them says equivalently that they form a basis of the vector space. So we are just ordering every basis. In fact, many times when we say a basis, we are talking about an ordered basis. That is clear from the context. When you make the matrix of a linear transformation with respect to a basis, then you are working with an ordered basis. Otherwise, you can't make the matrix. Whatever. So I'm just saying that collect all the ordered bases of the vector space V, and on this object we will define an equivalence relation, or first of all a relation, and then later we'll see that it is an equivalence relation. What is the definition? We say, or we write, that this ordered basis u1 up to un is equivalent or is related to the basis v1 up to vn if the linear map T which sends ui to vi, if the linear map T which sends ui to vi for each I, there is a unique linear map which does this. It has positive determinant, satisfies that its determinant is positive. Any such linear map will be invertible, so the determinant cannot be 0, and therefore the determinant would either be positive or negative. All right, so that's a relation. Is it an equivalence relation? So we claim that tilde is an equivalence relation. Okay, so why is that? It's very simple. We need to check reflexivity. Reflexivity is clear because if these two things are the same, the linear map that you get is the identity map, which has determinant 1 and hence positive determinant. So reflexivity is clear. Symmetry, well, if suppose this has positive determinant, well, suppose we choose two ordered bases and we assume that this is equivalent to that. Maybe I'll write this one, although it's very simple. So let this guy be equivalent to v1 up to vn and T be this linear map. What do we want to do? We want to show that v1 up to vn is equivalent to u1 up to un. All right, how do you do that? Well, what is the corresponding linear map that we need to check the determinant of? The corresponding linear map is nothing but T inverse. T inverse is the map which sends Vi to Ui. But if T has positive determinant, so does T inverse, and therefore we know that this is true. So let me not write all the details. And transitivity is very simple. It's just that the determinant of the product is the product of the determinants. And when I say determinant of the product, I'm talking about the composition of the linear maps. When I say product of two linear endomorphisms, I just mean their composition, because anyway, it has no meaning to multiply two endomorphisms. So transitivity is trivial. Everything is trivial. All right. So this is an equivalence relation, and an orientation on the vector space V is, well, how many equivalence classes are there? First of all, let's talk about how many equivalence classes are there. It is an equivalence relation. So the set of all the ordered bases would be partitioned into equivalence classes. The thing is, there are only two equivalence classes. Either the determinant of this map would be positive or it would be negative. There are only two possibilities. Okay. So, yeah. So maybe first we should prove that there are two equivalence classes. Claim tilde has exactly two equivalence classes. And the way we would prove it is the following. Suppose we pick some element in the set script B, and suppose we have two other things, V1 up to Vn and W1 up to Wn in script B, such that they are both inequivalent with U1 up to Un. So such that U1 up to Un is inequivalent with V1 up to Vn, and also inequivalent with W1 up to Wn. So if you pick two things that are not in the equivalence, well, if you pick two things which are not in the equivalence class of this guy, we would show that these two things are equivalent, and that will show that there are exactly two different equivalence classes. First of all, there are at least two different equivalence classes, because you can easily create, well, you just pick any invertible linear map whose determinant is -1, let's say, or negative, and then you can create something inequivalent to this guy. So I'll leave you to prove that there are at least two equivalence classes. And now we will show that if you fix some element of this of script B and choose two things which are not equivalent to it, then those two things are equivalent, and that will show that there are exactly two equivalence classes. How do you do that? You just use the definition. So we have the linear map S, which takes Ui to Vi, and we have the linear map T, which takes Ui to Wi. Both of them have negative determinant. They do not have positive determinant by assumption, so they necessarily have negative determinant because the determinant cannot be 0. They are invertible maps. And now the linear map which takes Wi to, or let's say Vi to Wi, what is that linear map? That linear map is, first you apply S inverse and then you apply T. So this is nothing but Ts inverse. So Ts inverse takes Vi to Wi, but what is the determinant of Ts inverse? It is the product of the determinants of these two things, but both of them have negative determinant, and hence this guy has positive determinant, and which shows the equivalence of these two guys, and that's it. So there are exactly two equivalence classes, and I'm out of space, unfortunately. So now we will say that an orientation an orientation of V is a choice of an equivalence class. So there are two possible orientations on any real vector space V. Okay. An oriented vector space, or we say V is oriented if we have fixed an orientation on it, if we have chosen an orientation for it. Stating this more formally would be an oriented vector space V is a real vector space V along with some omega, where omega is an orientation on V. So an oriented vector space V is a pair where V is some real vector space and omega is an orientation on it. Okay, so I hope the definitions are clear. Yeah. So maybe let's talk about the plane. I don't know. I don't have something very enlightening to say here. So the standard orientation, yeah. So maybe I should talk about the standard orientation on Euclidean spaces at least. So the standard orientation on Rn is the one given by this particular basis, by the standard basis, right? This basis has its equivalence class. That equivalence class is the standard orientation on Rn. Okay, and in the plane, we know what that is. This is E1 and that is E2. So E1, E2 in that order is the standard orientation. And for the space, for the three-dimensional Euclidean space, this thing, E1 and then E2, oops, and E3. So E1 first, E2 later, and then E3. This is the standard orientation. If you flip two of them, if you flip, suppose you say, talk about E2, E1, E3, what is the orientation of this guy? This is the opposite orientation. This is opposite to the standard orientation. If you flip two things, the determinant will flip its sign, right? So that was perhaps an observation to be made. If you pick some ordered basis, of course, this has its own orientation. The orientation of this guy, you just flip the, let's say, only the first two things, and everything else is in its own place. The orientation of this is the opposite. The determinant that you get when you make the linear map, V1 maps to V2, V2 maps to V1, and everything is just fixed, that will have negative determinant. Very easy to check. Okay, just make the basis of the linear map with respect to this particular basis and you'll see that. So that is what formally captures the right-hand rule of orienting your Euclidean space. This is the standard orientation, E1, E2, E3. And if you just flip the roles of E2 and E1, then you get the opposite orientation. So that is the formal way of capturing the right-hand rule. I encourage you to think about it a little bit. That is the best way to digest this fact. Okay, and now we can come back to the main business, which is about which is about talking about rotations of an arbitrary, well, no, I have something else to say. This slide is about something else. So first we will also talk about orientation on a hyperspace. So suppose we have some vector space, which is n-dimensional, some dimension, and it is oriented, so it comes with some orientation. Some orientation has already been chosen for it, and it is a real inner product space. To define orientation, you don't need an inner product, but let's say we have an inner product on it. Okay. Yeah. And now, if we have a hyperplane, suppose we choose a non-zero vector and consider the hyperplane perpendicular to it, meaning all those vectors in V which are orthogonal to the chosen vector V. In the picture, if this is our vector space, then if this is our vector V, then this is the hyperplane that is perpendicular to V, right? That's the picture. what we are going to do is we are going to define an orientation on this guy using the orientation that we have already chosen for the vector space V. Okay. So we will define an orientation omega on H. And how do we do that? Well, I also don't know. So let u1 up to un be some ordered basis, or un minus 1 be some ordered basis of H. Let's call it positive type. We will call this positive type. If this particular basis of the vector space V, if this has the same orientation as the one we have chosen for V. So nothing is going on. If you choose an ordered basis for H, you can just append that with V to get an ordered basis for the vector space V. You call the originally chosen ordered basis of H positive type if the new basis that you get for the vector space V agrees with the orientation of V that we had already chosen. Okay? And, well, suppose you choose two different things of positive type. Say u1 up to un minus 1 and u1 prime up to un minus 1 prime are of positive type, then they have the same orientation. And vice versa, and conversely. So this is a mathematical statement that we need to prove. If two ordered bases are of positive type, then they have the same orientation. And if they have, if they are not, or let's say if one is positive type and the other is, well, I have not made the correct statement. Let me just make it one-sided. This is the correct statement. If you pick two positive type ordered bases of the hyperplane H, then we claim that they have the same orientation. Similarly, if you pick two things of negative type, what is negative type? Well, any ordered basis that is not of positive type is negative type. So a same statement can be made about negative type bases. You pick two negative type bases, they will also have the same orientation. And a positive type and a negative type will have opposite orientations. But let's first focus on this much. All right, so why is this true? Well, how do we check for them being same orientation? We define this linear map from H to H, which sends ui to ui prime. This is our linear map. We need to check that this has positive determinant. Okay, define a map S from V to V, which is as follows. S, when restricted to H, just behaves like T, and it sends V to V. This is our definition of another linear map. All of these are linear maps. This is a linear map, this is a linear map, and the definition of T is this, or is given by this, because there's a unique linear map which does this, and similarly for S. We are saying that on H, S behaves just like T, and it fixes V. Now, since these are of positive type, we know that the determinant of S is positive. Because what is S doing? It is sending u1 to u1 prime, dot dot dot, un minus 1 to un minus 1 prime, and v to v. So this particular ordered basis is sent to that ordered basis. And by definition of positive type, these are both agreeing with the orientation of the vector space V, and hence S has positive determinant. So determinant of S is positive. All right. And now we want to show that determinant of T is positive, right? That is what we need to do to show that the chosen ordered bases have the same orientation. Well, let's make the matrix of T with respect to whichever basis we like. So let's make the matrix of T with respect to, or let's first make the matrix of S with respect to some whichever basis we want. Let's choose this basis, not whichever, but this basis, u1 up to un minus 1, and then a v. So we are making the matrix of S with respect to that, and that will look something like this. The last row will consist only of zeros, except here we will see a 1, right? Because what is S of u1? S of u1 has no component in V. S of u1 is lying in the hyperplane H, right? S of u1 is u1 prime, which is lying in H. So this will be a 0, and similarly up to un minus 1, we will get a 0. But S of V is V, so we'll get a 1 over here. And here there will be some garbage. And what about this guy? Here we'll see 0 all the way. This is what the matrix will look like. The determinant of this guy is positive. The determinant of this matrix is positive. That is the same statement as saying the determinant of S is positive. Which means what? The determinant of this particular square matrix is positive. Right? Because if you just expand out the determinant using this particular row, you will see that it is same as this determinant. But what is this matrix? This matrix is nothing but the matrix of T with respect to u1 up to un minus 1. Right? So the determinant of this matrix is positive, and hence the determinant of T is positive. So we have shown that if you have two positive type bases of H, then they are of the same orientation. Similarly, two negative type bases of H have the same orientation. And two bases of different types will have different orientation. That is an exercise. So the induced orientation on H is the one given by positive type ordered basis of H. The orientation, so the vector space V is inducing an orientation on H by means of its own orientation. There is an orientation on the vector space V, right? And that is inducing an orientation on this hyperplane H by means of its own orientation. Okay? So I hope this concept is clear. This is called the contracted orientation. You're contracting the orientation on the vector space V to get an orientation on the vector space H. I hope all of this is clear. Stay on it a little bit, even though we will not need it today, this concept, but I hope, or I guess we will need this in the next lecture. All right, so now we can come to the main point of our discussion, which I want to finish very quickly. Suppose we have a two-dimensional inner product space V, real inner product space V, and suppose we pick an oriented orthonormal basis of V. So the inner product space that we started with was oriented to begin with, and we pick an orthonormal basis which agrees with the chosen orientation. And now we can repeat the same ditto, same discussion that we had for the Cartesian plane. So if we have been given some theta in the set of real numbers, then we can define r theta as follows. It is going to look like this. Now I forget what was the formula, but let me try to remember. It should be something like that. This should be a minus, I think. And let me see, what was it? Should be sine theta. Yeah. So this is how you can define it, and you can see the similarity with the discussion on the Cartesian plane. It's just that artificially now this V1 is taking the role of E1 and V2 is taking the role of E2. That's all. And this was needed. If I may say so, suppose somebody is looking at the abstract vector space from this side, whatever that means, he would like to say that rotation by theta is going that way. While if you look at it from the other side, he might want to say that rotation by theta should go the other way, right? It should go the other way. So I don't know if that made sense, but that is the reason why you need orientation. That is another reason why you need orientation. Somebody looking at the vector space from this side and somebody looking from that side, for them to agree, they need to have agreed upon a chosen orientation. Otherwise, the natural notion of anti-clockwise rotation for the two people will be different. If you face a person, if two people are standing face to face, the clockwise direction for one person will be different or the opposite to what is the clockwise definition or clockwise direction for the other person. For them to agree, they need to choose an orientation on the plane which they are trying to rotate. That is one way to resolve that inconsistency. Okay, so the same discussion now you can carry forward. Whatever we did for the Cartesian plane can be done for this oriented two-dimensional real inner product space. All right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.